Now, to summarize what we have learned so far regarding deviations, residuals, the regression line, and correlation, the first term that is important in doing regression analysis is the deviation of a data or a data point, which is equal to y minus y hat. Okay? So this is y minus y hat. The directed distance y value from y hat, where y hat is the average of the y values. Okay, that is about the regression line. This is the y hat. These are the average of the y values. Okay. Next, the residual or residual deviation of a data point from the line y hat equals mx plus b is y minus y hat, the vertical directed distance of its y value from a given line. Right? So to represent, and we have been doing this since the first lecture on lesson 3-2. So to represent it, we have to form a line from here running through this, okay? And this is, let's say, our best fit equation according to regression analysis on your grapher. So what we're trying to say here is that we have the deviation of a data point xy, xy is y minus y hat. So where is our data point? Our data point is where the mean lies, right? So where is our mean? Our mean in this case is at y equals 16. So this is the mean. Okay? Now the data point is, of course, what are the data points here? Of course, the points in our data. And what are those points? These are our data points. This point, this point, this point, this point, and this point. These are our data points. Okay? So after regression, the let's say let's take a particular data point and let's take it this is our specific data point, for example. Okay, this one, and then this is the mean value, and this is the y. So our y is equal to this, right? And our mean is this. And where is our y hat? We're missing one point here. This is our y hat. Okay? So let me draw. Okay, my y hat is very small. So anyway, this is deviation before the regression. Where is the mean? This is the deviation before the regression. Y minus the value of the mean. So y minus y bar. Okay? And this is the residual after regression. Sorry, it's very small. We could have done better than that, but that's the best that we could do for now. So this is y minus y hat. This is the deviation or the residual. You call it a deviation when it's before the regression or when we are considering the mean. So this is the deviation. This is before regression. And when we do consider the values of y hat after regression, we call it residual. Residual because they are very small, or they are way smaller as compared to the deviations. So this is the residual, which is after regression. Okay, so I hope it clarified your thoughts on with respect to the deviation and residual. So again, a deviation is done before regression, meaning that you are comparing your y, getting the difference from your data point y minus the mean of the entire data for y. So you get the average of your y values. That's your y bar. Okay, that's your y bar. And then you get the difference between your y and your y bar. That is called deviation before regression. Okay, because it occurs before regression. Now after regression, when you did found a line which best fits the given scattered data, now the deviation from the data point to the y, okay, where is our y hat? This is our y hat, and this is our, where is our y? This is our y. Oh, okay. I think I made a mistake here. This is not y hat. Y hat is this. Okay? So the deviation after regression is what we call residual, when y is subtracting from itself the value of y hat. Okay? And y hat is taken from the best fit line through a regression data analysis using your graphical calculator. Okay, so I hope this enlightened you. Next, the sum of the squares of the deviations, or S's dev, is equal to the Riemann sum of y minus y bar square, where the summation symbol, the capital Greek letter sigma, means the sum of all values following the sigma sign. The sum of the squares of the residuals, and this is applicable to the residuals, so after regression. This is before regression. This is for the mean. Okay, is S is res, the Riemann sum, sigma, equals y minus y hat square. The linear regression line for a set of data is the line for which S is res is a minimum. Okay, remember this, it's a minimum. Okay, so when you compute your S is res, as we have shown in the previous lecture, like in here, you should be able to compute a minimum res. So in this case, you have 19.80. In here, you have 17.65. And in here, you have 17.6 for the same scattered data, which is this. And because the one that yielded the least S res is this expression or function expression, then this is the best fit line or best fit linear function, and this is our regression line. Okay, the linear regression equation is the equation of this line, y hat is equal to mx plus b. Next, the coefficient of determination. So this is the coefficient of determination. It's r square is equal to S's dev, or the deviation from the mean, the squares of the deviation from the mean, minus S's res, or the squares of the residual, the sum of the squares of the residual, divided by the sum of the squares of the deviation. And S's dev, okay, or the r square is the coefficient of determination, is the fraction of the s's depth that has been removed by linear regression. Meaning, when we did, as in here, these are our s's residuals, the squares of our residuals. But here, these are the squares of our deviations. So the fraction that is being removed as compared here, so you can see that in here, there is a big removal because this is our first square, which is the s's dev, and compare it to the s's rest here. So the fraction that is being removed from here going to the here to the encircled, to the yellow encircled box is very large. Okay, so that goes for the coefficient of determination. So the correlation coefficient R is the positive or negative square root of the coefficient of determination. So you have the coefficient of determination. For example, my coefficient of determination is, let us say, R square is equal to, let us say, let's say my coefficient of determination is 0.75. Then I get the positive square root of that, and that's my correlation coefficient R. And I will get the positive square root if the slope of the line is positive. And what are those slopes? Those that are increasingly upwards, such as this. So this is a positive slope, okay? And this is a negative slope because it goes down or it is decreasing. So in that case, your R will be negative, okay? And R is equal to 0 if, you know, they are totally, you couldn't really find the best fit line, such as in this case, which is circular. And it's very hard to, you know, get the best fit line for this, okay? Unlike here, that you could be able to identify the best fit line because, you know, these dots here are closing in to a certain linear line or a linear formation, right? But in this case, it's circular. It's totally circular. So R is equal to 0, meaning that the correlation coefficient is 0. So there is no correlation at all because it could be like that or it could be like that on the other side nodes. Okay? It could be like that, it could be like that. But it's pretty circular. Okay? Example number 1. Find SS dev and SS rest for the setups data in this section. Use the results to calculate the coefficient of determination and the correlation coefficient. How do you interpret the data for the coefficient of determination? So of course we are going to go back to the original data. And what are the data? We have X and we have Y. So these are my X values. And this is for my Y values. This is for my deviation. My mean is 16, right? So this is for the deviation squares. And this is for the residual squares. Okay, now first let's have a look at our X. Our X are from 2, 4, 6, 8, 10. And the data gives us, these are still the data for the setups that Mo did. Okay, so 8, 10, 19, 18, and 25. Y minus 16 squared, so our y is 8 minus 16, that's 8 squared, that would be 64. 10 minus 16, that's negative 6, square is 36. 19 minus 16 is 3, square is 9. 18 minus 16, that's 2 square is 4. 25 minus 16, that's 9 square is 80, 81. Now let's take a look at y minus y hat square. Our y hat for 2 is, let me have the table again. So this is our y minus y hat square, going back to the older uh, tables, okay, for lesson 1. So putting these values here for y minus y hat square, we have 0.16, 0.16, then we have 3.24, then we have 9.00, then we have 4.84, and then we have 0.36. Now, the reason why we have the same decimal figures here is that to preserve the number of what do you call this? The uniformity in the statistical value. So if you have 2 decimal points used for the entire column, then you should use the 2 decimal points for this column, y minus y hat square. Okay, now how do we solve for the square of the standard deviation? The square of the standard deviation can be taken from just getting the sum of this column here. So SS dev is just equal to the summation of this y minus y naught or y bar square. So just add all of this, 64 plus 36 plus 9 plus 4 plus 81, that gives us 194. Okay? And for the squares of the residuals, S is res, that's just the summation of your y minus y hat square. And in this case, it will give us 0.16 plus 3.24, it's 17.60. Okay, and this is the minimum, which gives us the best fit line for our data. So how do you interpret the value of coefficient? How do we solve for the coefficient of determination, the correlation coefficient? Now taken from here, your correlation coefficient is r, and this is the square root of the coefficient of determination. And the coefficient of determination is S is dev minus S is res over S is dev, which means that S is dev, so r square equals S is dev minus S is res over S is dev. So what is our r square? That would be 194 minus 17.60 over 194. Therefore, our r is equal to, or our r square is equal to 194 minus 17.60 divided by 194. That's equal to 0.909278. 0.909278. Now this is the portion that was cut, or the fraction of the deviation that was cut, the square of the deviation that was cut. Okay? So the remaining 9.07%. Now if you make it percent, this will be 90.92, let's say 93%, okay? Just multiply the r square by 100. It gives us 90.93%. So what about the missing 7 point or 9.07%? So there is missing 9.07%, right? So the missing 9.07% is due to other fluctuations in the data. Okay, there are, of course, there are other, fluctuations here, like other factors which are involved here. Okay, and those fluctuations, those factors which are external in nature, okay, uh, these are very small fluctuations from the tabular data here. But the correlation or the coefficient of determination r square pretty much indicates that there is a very strong correlation between the variables. Okay? Meaning that this variable y, or the mean y mean and y, and this y hat, these are the variables here, y bar and y hat, these are the variables here. There is a fairly strong correlation between them. Okay? So that is the value of your r square. So let us see about the correlation coefficient. Let us have our r. Where do we put our r? So let's put our r here. And our r is just the square root of our coefficient of determination. So the square root of 0.90928. Okay, square root of the answer will be 0.9535. So indeed, the coefficient of the correlation indicates it. It states, it's visible that there is a very strong correlation between the variables involved here. And we took the positive square root because look at your line. The regression line is increasing. The regression line says it. It's like that. And the data points are also increasing. They're going up. So that means that we should use our correlation coefficient r as the positive square root of the r square. Okay? That solves our example 1.